Most of us learned about electricity through a simple analogy. We are told that a continuous loop of wire acts like a pipe, and that electrical energy is a stream of electrons rushing through it like water. This model fails when applied to the alternating current power grid that runs your home. In an AC system, the electrons don't actually flow from the power plant to your house. Because the current alternates, the electrons inside those power lines simply wiggle back and forth 60 times a second. They stay in roughly the same place. This creates a paradox. If the physical charges never actually travel from the power station to your kitchen, how does the energy reach your toaster? Discarding the water pipe model is the first step to seeing how energy actually moves through the space around us. To see how this works, consider a circuit on a table. We have a battery, a switch, and a light bulb, separated by exactly 1 meter of physical space. Imagine the wires connecting the battery and bulb don't run straight across the table. Instead, they extend 300,000 kilometers into space before looping back. That is exactly 1 light second long. After you close the switch, how long does it take for the bulb to light up? Does it take a full second for the signal to travel the length of the wire? Or half a second? Or is it instantaneous? The answer to this puzzle reveals the hidden path that energy takes to reach its destination. In the 1860s, physicist James Clerk Maxwell realized that light and energy are composed of oscillating electric and magnetic fields. Later, John Henry Poynting proved that any time electric and magnetic fields coincide in space, energy flows through that space. This is the Poynting vector. When electric and magnetic fields cross, energy flux travels perpendicular to both. In a circuit, surface charges create an electric field, and internal current creates a magnetic field. Together, they force energy to travel entirely through the surrounding space. Wires act as a scaffolding for these fields, which carry energy through the air rather than through the metal itself. This theory was put to a multi-million-dollar test in 1858 during the attempt to lay the first transatlantic telegraph cable. William Thomson, also known as Lord Kelvin, believed electricity flowed like water through a tube. He and his peers ignored the role of the fields outside the wire. Because they didn't understand field theory, they wrapped the central copper wire in a heavy outer layer of iron to protect it from the ocean floor. The conductive iron sheath increased the line's capacitance, which distorted the electromagnetic fields in the space around the copper. The signal became a garbled mess, and the cable failed within weeks. This failure proved that blocking the space outside the wire stops the energy from moving, confirming that fields carry the power. Returning to our light second-long circuit, we can finally see why the length of the wire doesn't dictate the speed of the bulb. When the switch closes, the bulb turns on almost immediately, in about 3 nanoseconds. The electromagnetic fields established at the battery propagate through the air in all directions. Because the bulb is only 1 meter away, the energy reaches it immediately, rather than traveling the full 300,000 kilometer length of the wire. The energy takes the shortest path through the air. The long loops of wire are only there to establish the initial fields, but the power itself bypasses the loop. This physics is why our modern power grid looks the way it does. Utility poles hold wires high, keeping them away from the ground. This creates a large air gap that allows electromagnetic fields to travel efficiently without being distorted or absorbed by the Earth. Right now, electromagnetic energy is flowing through the air around every power line at nearly the speed of light. Flicking a light switch reconfigures the electromagnetic fields in your room, pulling power from the air directly into your devices.